We are done with electric fields for now. Now we're going to go on to the concept of electric potential energy. Again, very similar to gravity. We started out with the gravitational force, went to the gravitational field, and then defined gravitational potential energy. We're going to follow a very similar process to determine what the electric potential energy is. We'll begin with two charges with the same sign, both at rest, and they're both positive. Here's positive, here's positive. Q is at the origin, and we're going to start little q at infinity. In order to move q, little q, towards big Q, we need to apply a force opposite to the Coulomb repulsive force, right? Because these are both positive charges. They want to push each other away. So if we want to get this q to move this way, we have to apply a force in that direction. And that force has to overcome the Coulomb force, which is kqq over r squared. Note, this is not a constant force. The closer these charges get together, little r gets smaller, so the force gets greater. So we have to apply an increasing force in the left direction to bring these two charges together. Continuing on, recall that work is defined as work is equal to force times the distance that's parallel to the force over which the force acts. Later on in AP Physics, we'll talk about a dot product, which basically says you take the component of force in the direction that you're moving the particle, and you multiply those numbers together and you get work. Now, since we're bringing this charge in from infinity, we actually need to use calculus, because remember on the previous slide, we said that the force is not constant. It continually increases as it gets closer together. That means we're going to have to do integration, which you don't know yet, but you will soon. And then we will describe potential energy as the negative of the work done. And we'll assume that we have zero potential energy when these two charges are infinitely far away from each other. We will add up every little bit of force over every little bit of distance, and finally we'll come up with this equation where the potential energy is equal to K, Coulomb's constant, times the big charge times the little charge, divided by R. Notice this is very similar to the electric field equation, but for the electric field equation you had R squared in the denominator. Here we just have R. This is the equation for the potential energy due to two-point charges, which we will call big Q and little q, just to distinguish them, separated by distance R. Again, we kind of use the same technique to find the gravitational potential energy as we did here, which is nice. And the big benefit of using potential energy, just like in mechanics, energy, of course, is a scalar. It has no direction, no vectors, so it's a lot easier to do the math. We do care about the sign, okay? So it's either going to be negative or positive. But that's all. We don't care about the direction. We just find the distance away and we add or subtract them depending on the value of the potential energy, whether it's negative or positive. If you have a positive charge and a negative charge nearby and you want to calculate their potential energy, you use the formula, U is equal to KQ, but here we have a negative charge. So it's K big Q times negative Q over R, and we get negative KQQ over R. The physical meaning of this is that it takes work by an external agent to keep them from getting closer together, so we have a negative potential energy. You look at these two guys, they want to get closer together, opposites attract. So I would need to put work in to push either this guy that way or that charge that way. So we wind up with a negative potential energy here. If you have two like charges, for example, two positives or two negatives, you will have a positive potential energy. We use the equation here, potential energy KQQ over R, and in the case where they're both positive, we just get KQQ over R, which is a positive number. If both charges are negative, you can see how negative times negative is positive. You have the exact same potential energy. In this case, you need work done by an external agent. You have to have a force pushing them together because they want to repel. So if that's the case, we call it a positive potential energy. Now, don't worry too much about this, whether it's positive or negative or what it means. You just have to use this equation and the sign will naturally come out of it, and then you can say it's either negative or positive.